Hey guys, this video is about what are called pseudo rate laws. So when we have more than one reactant, the kinetics can get pretty complicated. So we have a little trick to simplify things for us. Because it ends up that if the concentration of all the reactants except one are in such a large excess, their concentrations will not change appreciably compared to the concentration of the reactant that is not in a large excess. And what that means is the concentration of everything but one species can essentially be held constant, and we can look at one reactant at a time. And that makes it a lot simpler. So let's look at the reaction between hydrogen ion, bromide ion, and bromate ion to form water and bromine. And it ends up that the rate law was determined experimentally to be this: first order in bromide, second order in hydrogen ion. And the way it was determined was the method we're about to look at, using pseudo rate laws. And so, basically what we do is we hold everything constant except one, do that experiment, get the order of that reactant, then do another reactant, keep everything else in large excess, make it constant, and then keep on going for every reactant. So, so let's say, okay, we're doing the one where we're figuring out the order of this reaction with respect to bromide ion. So we set it up so that everything else, all the other reactants, are in excess by far, like 10,000 times greater concentration or more. So what that means is, because the concentration of bromate and hydrogen ion essentially does not change, because there's so much of those that the amount that changes is lost in the significant figures. The rate is basically equal to some constant times the concentration of bromide, where that constant is equal to the rate constant times the concentration of the other two species. And we'll call that K prime. Okay. So now this looks a lot simpler, right? Rate is equal to K prime, concentration of bromide to some power, the order, what we're trying to find. Which means, right, if we can get this, if we can get N, and if we can find K prime, then we can rearrange this equation and solve for K, which is what we really care about. So the way we find the order with respect to that one species is in this set of conditions where everything's in excess except the one reactant we're studying. We make a plot of the concentration versus time, the natural law of the concentration versus time, and 1 over the concentration versus time. Just like, remember, we did with the integrated rate laws. Same idea. So if the plot of concentration versus time gives us a straight line, we know the reaction is 0th order in that reactant, in this case bromide, and the slope of that best fit straight line is negative K prime. Similarly, if a plot of natural law of the bromide versus time gives a straight line, it's 1st order in that reactant, bromide here, and the slope is negative K prime of that graph. Likewise, if a plot of 1 over the concentration of bromide versus time gives us a straight line, we know it's 2nd order in the bromide ion. The slope of the best fit straight line is positive K prime. Now, real quick, I didn't mention this before. 0th order reactants are just going to be pretty much an artifice of the conditions, because in a 0th order reaction, the rate doesn't depend apparently on how much stuff is there at all, but there has to be some stuff there for the reaction to occur. So it's certainly going to change once the reactants are gone, but we'll just deal with it like it is. All right, so what we do is, do our reaction, make our graphs, find the one that has the best fit straight line. So the slope, so what we're looking for is we're going to get the r squared for our straight line as well as the equation. The graph with the r squared closest to 1 is the graph whose points lie most closely on that line and is the straightest line, and that tells us the order. So let's look. Let's do an example. Okay, so we studied this reaction right here, the reaction between nitrogen monoxide and ozone, important in atmospheric chemistry. We did 2 experiments, okay? In the first, we set it up so that there's a large excess of ozone, and it was 1.0 times 10 to the 14th molecules per centimeter cubed. Second experiment, large excess of the other reactant, nitrogen monoxide, 2.0 times 10 to the 14th molecules per centimeter cubed. We got this data. We want to find the rate law, so we need to know the order with respect to each of the reactants, and the rate constant, K. So here's how we do it, guys. We make graphs. Now, if you were doing a homework problem, you do these graphs yourself. If you were doing a lab, you do these graphs yourself. If you're working in a lab, you do these graphs yourself. But here, to make it quicker, I did them for you. But normally you would do these. However, you should know this. On an exam, I will not ask you to make a graph. I will give you that information some other way. So in this top row here, what I have are three graphs of, with the ozone in excess, so we're studying nitrogen monoxide. So nitrogen monoxide concentration versus time, natural log versus time, 1 over the concentration versus time. When we look at the R squareds over here, 0.951, 0.9999, 0.939, the one that's closest to 1, the R squared, is this one right here. This is the natural log. That tells us, just like with the integrated rate laws, this is integrated rate laws, that the reaction is first order with respect to nitrogen monoxide. So that's a pseudo rate law because we sort of artificially kept the concentration of ozone constant. But it's real useful because now we know the order of the reaction with respect to nitrogen monoxide. And what the second experiment does, see, is we do the same thing, except now we keep the nitrogen monoxide in excess and we plot concentration of ozone versus time, natural log of concentration of ozone versus time, and 1 over the concentration of ozone versus time. Once more, it ends up that the R squared that's closest to 1 is the natural log, 0.979, 0.9999, 0.977. So that tells us, because this is natural log versus time, that this is first order also with respect to ozone. It could have been, 0th, first, or second, but it ends up, it was first order. All right, so now we know some real good information, guys. First of all, we know the order of this reaction with respect to both reactants, nitrogen monoxide and ozone, first order, which means we know the rate law. And we also, from our equations up here of these graphs, we know the slope of the best fit straight line, which means because these are both first order, the slope is negative k prime. So we know the value for k prime. It's negative of the slope. Negative 0.00180 is the slope, so k prime for this experiment is 0.00180 per second, and ozone 0.00360 per second. Okay, so let's see how we use that. So we know the rate law because we figured out its first order from the graphs in both reactants, so this is the rate law. The rate, when we kept the concentration of ozone constant, is equal to k prime times the concentration of nitrogen monoxide. We found k prime, its negative slope of that natural log graph, and so it's 0.00180 per second. Rearranging this guy, solving for k, it's k prime over the concentration of ozone. We know, remember, we set up this problem. If you look back at the problem, you can see that the concentration of ozone in this experiment was 1.0 times 10 to the 14th molecules per second, large excess. So we can plug in here, get our K, 1.80 times 10 to the minus 17th centimeters cubed per molecules seconds. Seconds comes down here, centimeters comes up on top. Likewise, if we do the same thing for the second experiment where the concentration of nitrogen monoxide is held constant at 2.0 times 10 to the 14th molecules per centimeter cubed, we get the same thing, right? So, and we should. K should be the same. This just shows you that it's the same. So now we know, well, everything we can about that, about the kinetics under those conditions. We know the rate constant, and we know the rate law. All right, so let's do an example where you get to practice this. So here's the setup, okay? So we have this reaction, 2A plus 3C goes to D plus 2A. It doesn't matter what the reactants and products are. We studied this reaction at a certain temperature, and we got the data that's in this table down here. Concentration of A was held constant, and it was set up in large excess to be 1.50 molar, which is much larger than the concentration of C, because concentration of C is 10 to the minus 5th, 10 to the minus 6, right? And it ends up, so we did another experiment, let's say. And in that experiment, we did this kind of data collection, and we found that the order of this reaction with respect to A is first order. So we already did this for A, and now we're doing it for C. What we want to do here, what I'm asking you guys to do is determine the rate law, so the order with respect to C. We already know the order with respect to A, and the value of the rate constant. So again, if you were doing homework, you were doing a lab, or you were out there in a real lab, you would do these graphs yourselves, but I did them for you. So here they are. Use them as you will. Go ahead and work it out, and when you get an answer, come on back. Welcome back, guys. All right, so when we look at these, we see that the graph, this is concentration versus time, natural law of the concentration versus time, and 1 over the concentration versus time. The graph that has the r squared closest to 1 is the 1 over the concentration versus time. So that tells us, right, that the order of this reaction with respect to C is second order. 1 over the concentration versus time is the most linear. All right, so knowing that, okay, we know the rate law. Rate equals K, concentration of A. Remember that other experiment we already did, we found that it was first order with respect to A, times the concentration of C squared. From the graph, we see that the slope of the line, of the best fit line for the 1 over the concentration versus time is 313.9. That means times 10 to the second right there. So that gives us our K prime. Our K prime is positive slope because it's second order, right? So K prime is basically 313.9 per second per molar. And that's equal to everything here, K concentration of A. Solving this for K, just dividing by concentration of A, K prime, we get 209.2 per second per molar squared. And so we know our K. And that's all there is to it, guys.